Here is that problem number 2, which deals with inelastic collision into to be more specific, with an explosion. All right. So we have an unstable nucleus with a given mass, which is initially at rest. So it tells us about the velocity, or the initial momentum of the whole system is 0, and thus it should remain 0 even after. And it disintegrates into 3 particles. One with a given mass will have a certain velocity along the y-axis. Another one with a given mass will have this speed along the x-axis. And we want to find the velocity of the third particle and the change in kinetic energy, all right? So what I did here, I put already the given information. So the mass, the total mass, the velocity before collision, the mass and velocity of one particle, the mass and the velocity of the other particle, and the mass of the third particle by just subtracting the 2 masses from the total mass. So what we're looking is for the velocity of the third one and the change in kinetic energy, right? So let's visualize it a little bit. So what we have here, okay, we have, this is the y-axis, this is the x-axis, and this is our A plus B and plus C. So what happened is this A is moving along the y-axis. We have B, which is slightly bigger, moving along the x-axis. So this is VA, this is VB, and therefore C should be somewhere here in the middle, right? VC. Okay, that's what it looks like. Okay, so what we're going to write here is that the momentum is conserved, right? So P of all of them together of M is equal to PA plus PB plus PC. So the momentum of the sum of the momentum of each and every one of them. Since it's in 2 dimensions, we're going to use the component form. So PMX and PMY is equal to PAX plus PBX plus PCX. So the momentum is conserved in the x direction, but is also conserved in the y direction. All right. Now what we are going to use here, let me minimize it a little bit. So we are going to, this is 1, 2, and 3. We know that PM is 0, right? So what we can do is I can use a table form or the equation, it doesn't matter. So for the x, now I have 0 equal to PAX, all right, so which is VAX times the x component velocity plus PBX VBX plus PCX, which is VCX. All right, and the other equation is on the y direction. Again, the initial momentum was 0, so therefore the y component is also 0. And then I write the components, okay, VAY, MB, VBY, and MC, VCY. Okay, however, VAX, so remember the particle A is moving along the y-axis, so VAX is 0, and the same with VBY is 0 because B is moving along the x-axis. Okay, so this becomes pretty straightforward. We get MCVCX equal to negative MB VB, right? Because VBX is VB. Okay, and for the y direction, we get MCVCY is equal to negative MAVAX, which is actually VA. So now we can solve for VCX to be negative MB over MC times VB, and VCY to be negative MA over MC times VC. So here are the components of the velocity of VC. So now we can find the velocity actually. So its magnitude is square root, as you remember, the component method, right? So it's VCX squared, so it's negative MB over MC VB squared plus negative MA over MC VC. Sorry, this is VA actually, I apologize. VA squared. Okay, and at this point, you can substitute numbers. You can find also the angle, and the angle, remember, is inverse tan of y versus x component, right? So it's M A V A over MC over MB VB over MC. They were both negative. So the angle theta is inverse tan. We know it's on the third quadrant though, right? Whatever we get from this tan, we know where our vector lies, and that is on the third quadrant, right? So when we describe it, so remember our vector is like this. This is negative VA, this is negative VB, and this is vector VC. All right, so the angle that we're finding is this one here. Okay, now at this point you just substitute the numbers. How do we find the change in kinetic energy? Well, is final minus initial, right? Initial kinetic energy is 0. So initial is 0. Okay, so which means that the change or the increase in kinetic energy, which is, by the way, done by a transformation of nuclear energy into kinetic, it's half of m, pretty much the kinetic energy of every particle, ma va squared plus half of mb vb squared plus half of mc vc squared. Okay, if you want to see something interesting, what's going to happen is I have half of ma va squared plus half of mb vb squared, and then plus half of mc. I remember what it was, right? It was the square root of ma va squared plus mb vb squared over mc, and all of it is squared. So delta ek is actually, and you can notice there that once I square it, the square root will go away. So I'm going to have half of ma va squared plus half of mb vb squared plus half of ma va squared plus half of mb vb squared. All right, so as you can see, that the kinetic energy of particle C is equal to the sum of the kinetic energy of particles A and B. Very interesting. All right, so it's 2 of the kinetic energy of A plus 2 times the kinetic energy of B. I just thought that that's interesting. All right, and again, I didn't put the numbers, but at this point, you can continue with the numerical answers, if you will. All right, I'm more interested in how we get the equations.